Right, so in 1925, two American physicists, Clinton Davison and Lester Germer, they performed the Broy's hypothesis experimentally and observed interference maxima when a beam of electrons was reflected by a nickel crystal. And so here's the experiment setup. And you can see we have an electron diffraction tube here. And yeah, and so this right here is the electron gun, or the heated cathode. This is the electron gun, and this here is the crystal, or the nickel crystal. And uh, when they fired up the electron gun, they observed a series of bright and dark rings right over here, which looks something like this. If you recall from chapter 4, this is really similar to how light behaved when it passed to diffraction gratings or through slits, right? And so therefore, from this experiment, and from the series of bright and dark fringes formed at the center of the screen, they concluded that electrons behave like particles and like waves, similar to light. And so we can actually write an equation for this to demonstrate this mathematically. So the electrons here, they're accelerated through a potential difference, right? So we know from chapter 11, chapter 10, if I'm not mistaken, that work is equal to the charge of an electron, E times V, which is the potential difference. And work, well, from classical mechanics, we know that work is basically changing kinetic energy. Therefore, kinetic energy is equal to E times V, and 1 over 2 mv squared is equal to EV, and hence and we also know that kinetic energy is equal to P squared over 2m, and so we can substitute this in here, and so we'll get P squared over 2m is equal to EV, and P is equal to radical 2 MeV. And remember that equation we got, yeah, this one. And so lambda is equal to h over radical 2 MeV. And so V here is our applied voltage. So applied voltage V, if we decrease our voltage, our lambda increases. Vice versa, if we increase our voltage, our lambda decreases. And so there is, in essence, a inversely proportional relationship between the voltage applied to accelerate that electron and the wavelength formed, the wavelength of that electron wave.